Okay, today we're going to learn about the quotient rule. Yesterday we learned how to find the derivative of the product of two functions, and today we're going to learn how to find the derivative of the quotient of two functions. So our learning goals for today are: number one, we're learning to differentiate the quotient of two functions, and secondly, we're learning to find the slope of the tangent to a rational function at a specific point. The quotient rule tells us how to differentiate or find the derivative of functions such as f at x equals x cubed plus 2x minus 3 over x squared plus 5x. These are called rational functions because the denominator is a function of x. Okay, so yesterday we learned how to find the derivative of product of functions, today quotient of functions. So if f at x and g at x are both differentiable functions, then we could define capital F at x to be f at x divided by g at x. So a function of x divided by a different function of x. We say it's differentiable as long as the denominator is not equal to 0, obviously, because we can't divide by 0. We can prove that f prime at x, so the whole entire big function, so capital F prime at x, is equal to little f prime at x times g at x minus f at x times g prime at x all over g at x squared. And I'm going to prove this to you using the product rule, actually. So here's, if we start off saying that defining f at x to be little f at x over g at x. And then I'm going to solve for little f at x here. So if I multiply both sides by g at x, I get that little f at x equals g at x times big F at x. Or I could also write that as f at x equals big F at x times g at x. All right, so based on yesterday, we learned that to find the derivative of the product of functions, or little f prime at x, it would be the derivative of the first function, which is f prime, big F prime at x, times the second, which is g at x, plus the first function, which is big F at x, times the derivative of the second function. So that's just using the product rule. But this is actually what we're trying to find, big F prime at x. So now what we're going to do is use just algebra to get big F prime at x by itself. Okay, so what we're doing is we're proving that this formula up here is true. And that's how you find the derivative of the quotient of functions. So first, we're going to subtract big F at x times g prime at x from both sides. So we get little f prime at x minus big F at x times g prime at x equals big F prime at x times g at x. Before we want to get f prime at x by itself, we're going to use the fact that we know that, so I'm going to use blue to outline this, we know f at x is equal to, big F at x is equal to little f at x divided by g at x. So we can substitute that in on this side. So now we've got f prime at x minus f at x over g at x times g prime at x. And that's equal to f prime at x, capital F prime at x, times g at x. We're still trying to get big F prime at x by itself. So even again, we're just going to leave this g at x here for now, because now it looks like we're subtracting something that has a fraction. So in order to do that, we need a common denominator. So our common denominator, if we look at the denominators here, this one has got a denominator of 1, and this one has a denominator of g at x. So our denominator is going to be g at x. So we're going to make both of these fractions out of g at x. And on this side, we've still got big F prime at x times g at x. Okay, so This one, we had 1 in the denominator, so we had to multiply the denominator by g at x, so we're going to have to multiply the numerator by g at x. Here, the denominator already was g at x, so the numerator is f at x, g prime at x. Okay, so still, we're going to simplify on the left side by subtracting the numerators over the common denominator. So that's little f prime at x, g at x, minus f at x, g prime at x, all over g at x, equals big F prime at x, g at x. Finally, we're ready to get big F prime at x by itself. So we're going to divide both sides by g at x. So we're dividing a fraction by a non-fraction. So we know that that rule is multiply by the reciprocal. So now we've got big F prime at x equal to, so I'm going to show you this out long and then I'm going to arrow it over. So little f prime at x, g at x, minus f at x, g prime at x, over g at x, and then times, so we're dividing here, so we're multiplying by the reciprocal, 1 over g at x. So then here I'm arrowing over, so that means big F prime at x is equal to, so if we multiply the tops together, we get f prime at x, g at x, minus f at x, g prime at x, all over here we multiply the bottoms together. Look at the bottoms. They're both g at x's, so we get g at x to the power of 2. So that's why it's in square brackets there, g at x squared. Okay, and then how you say it so that you remember it is when you use the quotient rule and you find the derivative of the quotient of two functions, it's the derivative of the first times the second minus the first times the derivative of the second, all divided by the second squared. Okay, so let me say that again. Derivative of the first times the second minus the first times the derivative of the second, all over the second squared, which is what I said I was going to prove to you at the start of the proof, way up here. So that's the formula. And as we go through the examples, we're going to say that formula to ourselves so it becomes second nature, just like the product rule should become second nature for you. Okay, so here we're going to go on to the first problem. So the first problem says we want to differentiate, which means find the derivative. So and the function is f at x equals 3x minus 4 divided by x squared plus 5. So we're going to do the similar chart that we did when we did the product rule. So we're going to label what our first function is, what our second function is, the function, and the derivative. So our first is going to be the top function, 3x minus 4. The second is going to be the bottom function, x squared plus 5. The derivative of 3x minus 4 is 3, and the derivative of x squared plus 5 is 2x. Okay, so now we're going to use the quotient rule. So stay with me here. So here we've got, and we do that same crisscross pattern. So those correspond, and those correspond, just like they did with the product rule. So we're going to think about this. Derivative of the first times the second. So that's the blue. Okay, derivative of the first times the second. Is there a nice way to write that? Yes, monomial term out front. So 3 times x squared plus 5. Derivative of the first times the second. Minus in the formula. Minus the first times the derivative of the second. Is there a nicer way to write that? Yes, monomial term first. 2x times 3x minus 4. All over the second, which is x squared plus 5, squared. Okay, so what you've done right now is the calculus. You have found the derivative. Anything you do from here on is just simplifying your derivative using algebra. Okay, so in this case, we can simplify the numerator by distributing and collecting any like terms that come up. So we'll do that. So I would get 3x squared plus 15 minus 6x squared plus 8x all over here. I'm not going to expand that because what you're always going for in this unit is what we call simplified factored form. So the bottom is already in factored form because it's the product of two factors, x squared plus 5. So we would not want to expand it. Okay, so I've got like terms here that I can combine. And I'm just going to put it in this order where I have my x squared term, then my plain x term, then my constant term. And then what you always check for in your numerator is to check to see if you could factor it. So check to see if you can factor. So in this case, if this numerator were factorable, it would be factorable by decomposition because it looks like a complex trinomial. So you would need two numbers or terms that multiplied to negative 45 x squared and added to positive 8. So if you think about them, 1 and 45, definitely not going to work. 2 doesn't go in evenly. 3 and 15, not going to work. 4 doesn't go in. 5 and 9 doesn't work. So you can see that this is an unfactorable trinomial. So then you're done the question. Okay? So that's as simplified as you can and factored as you can make this answer. So there's your derivative. So if you want to box up your answer, you're done that one. Okay, on to the next question. So we want to find the derivative or differentiate g at x equals x squared plus 2x minus 3 over x cubed plus 1. So you're going to start off with the chart again. First, second, function, and derivative. So what's the first function? That's the one in the numerator. So x squared plus 2x minus 3. Second function is the one in the denominator, x cubed plus 1. And then you need to find the derivative of each of those. So derivative of x squared plus 2x minus 3 is 2x plus 2. And the derivative of x cubed plus 1 is 3x squared. And I want to use the same color coding, so we're going to do these correspond and these correspond. And as we're going through the product rule, or the quotient rule, sorry, we're going to say out what we have to do here. So g prime at x is equal to the derivative of the first. So here's the first, here's the derivative. Derivative of the first times the second. Is there an order that would be preferable? They're both binomials, so it doesn't matter. So 2x plus 2 times x cubed plus 1. Then there's a minus in the formula, minus the first times the derivative of the second. Here there is a monomial term, so that's going to go out front. All divided by the second squared. Okay, so there's the calculus. The calculus part is done. Now we're just on to the algebra. So in order to simplify the numerator here, we've got to expand two binomials by using FOIL here. And then here, just the distributive property. But then we're going to collect like terms and see if there's any factoring that can be done in the end. The bottom is already in simplified factored form. So if you're doing FOIL here, you're going to get 2x to the fourth plus 2x plus 2x cubed plus 2. Then remember to carry through the minus when you distribute here. So it's going to be minus 3x to the fourth minus 6x cubed plus 9x squared all over x cubed plus 1 squared. So let's look for like terms now in the numerator. So g prime at x is equal to, so anything else with a fourth? Yes. So I've got negative x to the fourth. Those are taken care of. Let's look for cubes next. So 2x cubed minus 6x cubed is negative 4x cubed. Those are done. Squared, yep, plus 9x squared plus 2x plus 2 all over x cubed plus 1 squared. And then that is not factorable by grouping. It may be factorable by long division, but we are not going to go to that length to do that. So in this case, you would be done this question and ready to try the next one. Ha. Okay. Y equals the square root of x divided by x squared plus 1. We want to find the derivative, so we're going to start off with our first, second function derivative. So our first function is root x, but I'd rather write that as x to the power of 1/2 because then it's easier to differentiate it. And then the second is x squared plus 1. So the derivative of x to the 1/2 by the power rule is 1/2 x to the negative 1/2. Okay? And the derivative of x squared plus 1 is just 2x. And again, we have our correspondence. So this time we'll just call it y prime. So y prime is equal to the derivative of the first times the second, monomial term out front. So 1/2 x to the negative 1/2 times x squared plus 1 minus in the formula. They're both monomial terms, so I'll do 2x times x to the 1/2 all over the second squared. So we know right away this one's not in simplified form because we have a 3-layer fraction. We have a 1/2 in the numerator and our x squared plus 1 squared in the denominator. So this is one of our first times we've come into complex simplifying here, complex factoring. But whenever there's a fraction in the numerator, that's being factored out for sure. So 1/2's being factored out. Then I'm gonna compare constant by constant. So 1/2 and 2, I'm gonna factor out 1/2. Then I'm gonna look at my x to the negative 1/2 and my plain x, and I'm gonna take, and my x to the 1/2, and I'm gonna take the exponent that's smaller. So what's smaller, negative 1/2 or positive 1/2? Negative 1/2 is, so we're gonna common factor that out. So here's our two big chunks. So in the first scoop is this term, and in our second scoop is that term. And what we want to do is divide each big scoop by this common factor of 1/2 x to the negative 1/2 and see what goes in our brackets. So if we divide this first big scoop by 1/2 x to the negative 1/2, the 1/2 x to the negative 1/2 divides out, and you're just left with x squared plus 1. Here, if we divide this big scoop by 1/2 x to the negative 1/2, first of all, we have to do negative 2 divided by 1/2. So that's going to be negative 4. Then I'm going to do, I've got the x here, this x here. And then x to the 1/2, I'm going to do this off to the side. Hopefully you can see it. So I'm thinking x to the 1/2 divided by x to the negative 1/2. Okay? And using the division rule for powers with the same base, you keep the base and subtract the exponents. So you get x to the 1/2 minus negative 1/2. So x to the 1/2 minus negative 1/2 is x to the 1/2 plus 1/2, or x to the 1. So when I divide this by this, I get another x all over x squared plus 1 squared. So let's go back over that again. So I looked at my number parts, 1/2 and 2, and I took the fraction out. Then I compared my powers of x, so I have x to the negative 1/2 and x to the positive 1/2. Chose to factor out the smaller exponent like we normally do in common factoring. Then I have two big terms here because these three things are all multiplying together, so they make one term, and then these three things are all multiplying together, so they make the other term. And I'm going to divide each one of these scoops by 1/2 x to the negative 1/2. That's how you common factor and see what ends up in the bracket. So when I divide this first big scoop by 1/2 x to the negative 1/2, the this part cancels away and you're just left with x squared plus 1. When you factor the next big scoop by a half x to the negative 1/2, the negative 2 divided by half gives you the negative 4. The x stays, and then x to the 1/2 divided by x to the negative 1/2. We did this off over to the side, gave us x to the power of 1. Okay, so that's how we got that. So now, really on the top, all we have is multiplying, which is what we want. That's called factored form. So on the top, we've got a half times x to the negative 1/2 times this whole bracket, which we can simplify a bit if we want to, but it's all multiplying. So when things are all multiplying and dividing, we can make it into just our 2-layer fraction here. We can keep that 1 on top that we don't need to show and move the 2 to the bottom. We can also move the x to the negative 1/2 to the bottom and make it x to the positive 1/2. So then what's left on top is x squared plus 1 minus 4x squared. And then to write it nicer than that, we can collect our x squared terms in the numerator. So we would have negative 3x squared plus 1. And then also, rather than writing x to the 1/2, we can write root x. So there's our derivative. So y prime is negative 3x squared plus 1 all over 2 root x times x squared plus 1 squared. Okay, so this is simplified factored form. And again, as I've said from the beginning here, this calculus step usually isn't the part that people find challenging. It's the algebra to get from here all the way down to this answer that you're going to see in the back of the textbook. That's the difficult part. So the algebra is what's difficult usually, not the calculus. Once you've got the quotient rule down, you can get the derivative, but you have to work hard and keep practicing so that you are able to simplify it down to the answer in the back of the book. All right, so we'll be doing this more over the next 3 or 4 days, especially once we learn the chain rule. All right, so the next question. Find the equation of the tangent line to the curve y equals 2x over x squared plus 1 at the point where x equals 0. Okay, so equation of the tangent line, first of all. Let's pass it around instead. So in order to get the equation of the tangent line, you need to know the slope of the tangent to this curve at the point where x is 0. Okay, so what we could do is find y prime, which means the slope of the tangent anywhere, and then we can replace x with 0 to find the slope of the tangent at 0. So if we want to find y prime, we have to do our first, second function derivative. So our first function is the top function, 2x, and our second is x squared plus 1. Derivative of 2x is 2. Derivative of x squared plus 1 is 2x. Okay, so y prime. Derivative of the first times the second, so 2 times x squared plus 1, minus the first times the derivative of the second. Well, I can multiply those together in my head. 2x times 2x is 4x squared. All over the second, x squared plus 1 squared. Now, if this was just a question differentiate or find the derivative, you'd have to simplify this. You'd have to distribute and collect like terms. But since they just want the equation of the tangent line where x equals 0, we could now just substitute in 0. So we can find y prime at 0 by setting all our x's to 0, which is going to make this easy, because here we would have 0 squared plus 1, which is 1, minus 4 times 0 over 0 squared plus 1 squared. So we end up getting that y prime at 0 is just 2. 2 minus 0 over 1, which is just 2. So now we know the slope of the tangent is 2. And we also need to know a point. Well, we know the x for the point has to be 0. And we can find out the y value by plugging in. Make sure you can see that in the video here. So I'm just plugging in y equals 2 times 0 over 0 squared plus 1 is going to give me 0. So the point 0, 0, which couldn't be easier. So now we find the equation of the tangent line. We could just use y equals mx plus b, where we know m is 2, x is 0, y is 0, so that we can figure b out. And we end up getting b is 0. So then we can say, therefore, the equation of the tangent line is y equals 2x plus 0. You don't need to show the plus 0. Okay, nice, easy equation of a tangent line. All right. So in the case where you're doing it for a purpose, like to find the equation of the tangent line, no need to simplify unless you want to. Okay, some people just like to do it for fun. I think I liked to do it for fun when I was in high school. Okay, so question 3. Find the coordinates of each point on the curve f at x equals 2x plus 8 over root x where the tangent is horizontal. So we want to be able to interpret. What does it mean where the tangent is horizontal? Well, horizontal tangents have a slope of 0. So it means the slope of the tangent is equal to 0. Okay, because horizontal lines have a slope of 0. So in other words, we want to know where f prime at x is equal to 0. So in order to know where f prime at x is equal to 0, we first need to know what f prime at x is. And in order to do that, we're going to use the quotient rule because f at x is a quotient of functions. So we need our first function, our second function. Fill out our table here. So our first function is 2x plus 8. Our second, I'm going to write as x to the 1/2, so it's easier to find the derivative of. The derivative of 2x plus 8 is 2, and the derivative of x to the 1/2 is 1/2 x to the negative 1/2. Okay, so f prime at x is going to be the derivative of the first times the second, so 2x to the 1/2, minus the first times the derivative of the second, monomial term first, all over the second squared. Okay, so, and I know I want f prime at x to equal 0. Because I'm going to be solving for x, you probably do want to simplify to make it easier to solve for x. So again, I'm looking at this as one scoop and this as my other scoop. So from those scoops, see, those are multiplying. All these three things are multiplying. I'm looking at my 2 and my half. My half is going to be factored out. I'm looking at x to the 1/2 and x to the negative 1/2. Smaller exponent's going to be factored out. And that's all they have in common. So that's my common factor. And now I'm going to divide each scoop by the common factor. So 2 divided by 1/2 is 4. X to the 1/2 divided by x to the negative 1/2. We did that earlier, but I'll do it again off to the side here. So x to the 1/2 divided by x to the negative 1/2 is x to the 1/2 minus negative 1/2, which is just x to the 1. Okay, so when I divide x to the 1/2 by x to the negative 1/2, I get plain x, which is nice. So then minus, so see this 1/2 x to the negative 1/2 here and this one here. When I divide this by this, I get 1 because they're exactly the same. So I'm going to get minus 1, but still times 2x plus 8. All over, now in this case, x to the 1/2 squared is x. Okay? All right, so now I've got enough to make a 2-layer fraction here instead of a 3-layer fraction because everything's multiplying on top. I can have my x down here. I can bring that x to the negative 1/2 down and make it root x. I can write my 2 in the bottom. And then I've got my 1 still on top, which I don't need to write. I've taken care of this and this. On the top, I've got 4x minus 2x minus 8. The lovely thing about setting something equal to 0 is I can multiply both sides by the denominator. I'll do the same thing on this side. But we know that anything times 0 is still 0. So all of a sudden, this side's still 0, but those divide out. So on this side, I'm just left with 2x minus 8. And then I'm solving for x because I want to find out where is the slope of the tangent 0. F prime at x is what means the slope of the tangent. Set it equal to 0. Solve for x. So I'm going to add 8 to both sides. Divide both sides by 2. And I get that x equals 4. Now read the question again. It said find the coordinates of each point. So I know that on the curve where the tangent is horizontal. So I know the tangent's going to be horizontal when x is 4. But that's not the coordinates of a point. That's only the x value. So to find the y value, I need to find f of 4 by substituting it into the original equation. So I'm using this one right from the top here. Finding f of 4. So 2 times 4 plus 8 over root 4. And that's going to give me 16 over 2, which is 8. And then I can write my statement out. So therefore, the tangent is horizontal at the point 4, 8. Okay, so let's go back over this question. Find the coordinates of each point on the curve. F of x equals 2x plus 8 over root x, where the tangent is horizontal. Sorry about the dog. All right. So first we found f prime at x. We set it equal to 0. We factored in order to help solve for x. Multiplied both sides by the denominator, which was a smart thing to do since one side was 0. Solved for x. And then substituted x into the original function to find the corresponding y value. And that was our point. Okay, question 4. The number N at T of new cars sold per week in Canada, T weeks after going on the market, is given by the function N at T equals 300T squared over 1 plus T squared, where T has got to be between or including 0 and 10. How many cars are sold in week 3? Okay, so in these word problem questions, it doesn't say anything about rate of change. Doesn't say average, doesn't say instantaneous, doesn't say anything about rate of change. It just says how many cars are sold in week 3. So you need to know that that's an easy question. They're just asking you what N of 3 is. Okay, so we're going to replace T with 3 in the function they give us and work that out. So that's going to be 300 times 9, which is 2,700, over 10, which is 270. So therefore, 270 cars are sold in week 3. Okay. B says, at what rate is the number of sales per week changing after 3 weeks, after 5 weeks? Okay, so now all of a sudden rate is involved. It doesn't say average, so we assume instantaneous. And now we have to find the derivative. Okay, so I did leave you room on the next page to go over, so we'll probably have to do that too. So we have to find the derivative, n prime at t. So in order to do that, we need our first, second function derivative. So first, second function derivative. So the first is 300t squared. The second is 1 plus t squared. derivative of the first is 600t, and the second derivative of the second is 2t. Okay, so n prime at t is the derivative of the first times the second. So I'm going to put my monomial term first. Minus, these are both monomials, so we can multiply them together. Minus the first times the derivative of the second is going to be minus 600t cubed. All over the second squared, so 1 plus t squared squared. Now, you don't need to simplify this one out because you're finding it at 3 and 5, but like I can see just by looking at this, so it makes me excited that I'm going to get 600t cubed here, and it's going to subtract with that one. So we want to do it even just for the fun of it. So we're going to get 600t plus 600t cubed minus 600t cubed, because that's so fun. They're going to add up to 0. Over 1 plus t squared squared. Okay, so now we're going to go on to the next page. I've run out of room, so you've probably run out of room. I'll try to keep this in camera view, this last part here. Okay, so now we know n prime at t is 600t over 1 plus t squared squared. It's a nice looking derivative. Now that we know that, make sure you've got it. We have to find n prime at 3 and n prime at 5 because it wants to know the rate at 3 weeks and 5 weeks. So that's easy now. So n prime at 3 is equal to 600 times 3 over 1 plus 3 squared squared, which is 1800 over, that's 9, 10 squared, 100. Which is 18. It's got to have units, so it says at what rate is the number of sales per week, so it's 18 cars per week. And then we want to find n prime at 5. N prime at 5 is going to be 600 times 5 over 1 plus 5 squared squared, which is going to be 3,000 over, that's 26 squared, which is 676. And if you do 3,000 divided by 676, you get approximately, to the nearest car, 4 cars per week. Okay? So, and then if you want therefore statements for these, therefore at 3 weeks, I don't know, can you see that up there? The rate of change is 18 cars per week, and therefore at 5 weeks the rate of change is 4 cars per week. Okay, so there's a word problem that involves the quotient rule.